Hello, everyone. I'm super excited and happy to be here today, uh, mostly because I find it very important to break down complex concepts for our community and external communities. And this is because I'm very sure that a lot of people are not even aware of what can be done with our technology. But yeah, let me start this properly. I'm Mihna. I lead the community team here at Oasis, and I'll be today's host. Of course, I'd like to welcome everyone and encourage you all to ask any questions you might have during the event. We'll try to answer all of them at the end, of course, if we have enough time. So today's event will be focused on our latest upgrade, the upgrade to Oasis Core 24.0. We'll break down all the improvements it brings to the table and, of course, talk in depth about the most important aspects of this upgrade. And today I'm joined by our incredible director, Yorne Kos. And Yorne, I'll let you introduce yourself to our audience.
Hey, yeah, thanks, Mina. Oh, I need to introduce myself. Okay, for the, it's been a few of these. Right, so I'm Rene. I'm the director of the Oasis Protocol Foundation, and I also am the tech lead for the Oasis core technology. So yeah, today we'll be talking about the upgrade. And as Mina mentioned, if you have any questions regarding the topics we will discuss today or anything else, feel free to reach out.
Thank you, Yorne. Okay, so as I've mentioned in the beginning, last month saw the Oasis Core 24.0 upgrade, the Eden 24 upgrade, which actually passed with a 76% voting stake. And Yorne, could you tell us more about this upgrade and what features it brings to the table? Can you hear me?
No, I can. I'm not sure. Do I have problems or is it on your end?
I can hear you properly.
Okay, cool.
I was asking if you can tell us more about the upgrade and what features it brings.
Sure. So I guess maybe the first thing about the upgrade is that nobody noticed that it even happened except node operators, maybe. But yeah, everything went smoothly, and that's I think an important part of this whole process. It should be seamless for the users and developers and everyone. And this is something that we want to commit to going forward. So no more breaking upgrades and more frequent upgrades and so on. So I guess about the upgrade, like the contents of it, there's a few things. Some are focusing on improving security, some are new features, some are performance improvements, and also there are some bug fixes. So maybe I can dive into this briefly, maybe some are more boring than others, but also no less important. The first one that I would mention is more of an accounting thing. It's increasing certain parameters. These are basically two things. One is the maximum transaction size and the maximum block size in the consensus layer. And the reason why this is needed is basically to accommodate larger node registrations, which are required by using the new DCAP remote attestation scheme, especially in the case when the nodes are running multiple runtimes at the same time. And going forward, we'll be also able to add more compression so that these transactions can also be smaller as soon as we have the on-chain remote attestation collateral registry that will also make things more robust and independent of the vendors. Then I guess one of the much anticipated security features is activating initial support for the CHURP key manager instances. We'll go into more detail later on. So this basically enables the consensus parts that allow managing CHURP key manager instances and basically allowing the key manager runtimes to utilize CHURP. Then there's also a minor feature that we slipped in. It's called the Vault service. It's basically a simple multisig service for the consensus layer, which makes some of the management operations easier as it can be governed by a simple multisig. And yeah, the CLI support for that is upcoming, but yeah, that should be useful for node operators and anyone that is operating runtimes and so on. Then there's two things related to governance. One is adding human readable metadata into governance proposals, which is a minor usability improvement so that block explorers can actually show more interesting stuff for governance proposals. And then there's a small bug fix related to voting, where there was an issue where the delegators would need to go through some extra hoops to vote, but now that should actually be fixed and work as designed. Then there's the performance optimization part, and that is another thing that's present in the new Oasis core release. It's the improved storage engine called Pathbadger, which we'll also mention a bit later on in more depth. Basically, the idea is that the nodes will run faster and require less disk space. This is achieved by changing the on-disk storage format. So that should be good news for the node operators, as it will require less resources and will be able to handle more queries, and also good for users and so on. And obviously, this is just the first step. We have further optimizations planned. Maybe that's a quick summary. Hopefully, I didn't forget anything, but yeah.
That's a lot. That's a lot of improvements and new features. And the multisig is that similar to Oasis Safe? Will it have a UI interface or anything, or just everything is done on
right?
chain?
So this is, yeah, that's a good question. So like this is indeed very similar to what's so in Sapphire there's Oasis Safe, which is what should be used by most users. So this multisig in the consensus layer is maybe more for node operators and runtime operators, so more geared towards network operations, as most people should be doing everything in the paratimes, so in Sapphire and so on. So yeah, the initial interface will be the CLI interface, yeah, and then we'll go from there.
Okay, got it.
So
I figured
basically
as
we
much,
have,
but
yeah, most of the operations that you can do on the consensus layer are actually possible from the paratimes. So for example, from Sapphire, you can do things like staking and so on, and then you can leverage the existing like Oasis Safe and so on to manage that. So no need for, yeah.
Oh, yeah. Nice. Okay, and you mentioned Pathbadger. That's related to prefix trees, right?
Sure.
How does that improve speed and the space requirements for node
so
operators?
maybe a bit of background, like all of the state in our blockchain or in most blockchains is stored inside like our authenticated data structures. In our case, we're using a Merkle-Patricia trie, which is, as you said, like a prefix trie. So this is basically a cryptographically authenticated data structure where it can ensure integrity of all of the state that's contained within. So it's basically on the outside, it looks like a key value store, but where you can actually prove that certain values have, certain keys have certain values just by knowing the root and the path to the leaves. So this is the basis of all of the state management that happens both in the consensus layer and also in all the paratimes. And we've had this since the beginning because we need somewhere to put all the state. Like this tree actually contains like things like all the balances, all the smart contracts, all of the state and so on. And to make things easier to implement, we leverage an existing key value store, which is called Badger, when putting things on disk. And now we had the old storage backend where basically every node in the trie was stored in this underlying key value store by using the hash of the node as the key. Obviously, this is simple, and the reason why it's like that is because of legacy reasons. It was quick to implement, and so it stayed like that. But the problem with that is that this makes basically these nodes, so the nodes are like in an internal implementation detail of the data structure. They're like referenced in Merkle proofs, and they're also contained, like the leaves contain the actual values. So this makes them scattered randomly on disk because they're using the hashes as the keys. And basically this decreases performance because there's no locality, and basically more blocks need to be fetched from disk when traversing the trie. So if you imagine during a key lookup, multiple of these nodes on the path from the root of the tree to the leaves needs to be fetched. And if they are like, if there's no locality, basically a lot of these block fetches need to happen from disk, and this adds latency. So with the new storage layout, with the new storage backend, we changed the layout to make this process faster. So instead of using hashes, basically we used two monotonically increasing counters were referring to nodes. So this makes things a bit more complicated, because previously you could just, compute the hash of the node and then just use that as a reference, but now you cannot. So there's a bit more bookkeeping, but in the end, this actually makes things much faster because it retains locality. And also it makes the database slightly smaller. So it's the best of both worlds.
Yeah.
So yeah, I mean, currently the Pathbadger storage backend is experimental in the sense that it needs to be explicitly enabled on nodes via configuration. But like any node operator can enable the new backend, and it should actually work. We're running most of our nodes in production with the new experimental storage backend. And yeah, the only caveat here is that this requires a resync of state. If you switch the backend, the node will need to resync, which takes a bit of time. So yeah, ideally you can spin up a new node and enable the backend and then just switch over. Yeah. Right,
So
and that's
we should promote this.
Yeah, we should. But also in a way where people are aware that it takes like the right procedure to actually do the upgrades and so on, so that we don't have all of everyone upgrading at the same time, like to the new storage backend. Cool.
Okay, so this basically fixes a lot of issues, including fragmentation for disks, and yeah, now I understand how it improves
things
speed.
like the database needs to do periodic maintenance, so to say, like to flatten the structures on disk and do garbage collection. And this new layout also makes this process faster and less burdensome on disk I/O. So yeah, it's a win-win in every sense. Yeah.
I find it amazing the small things you guys think of to improve life for everyone.
Yeah, small things, but the implementation is a bit more complex.
I can imagine. I can only imagine. Okay, so I think the most important feature of the upgrade is, of course, runtime off-chain logic, or ROFL. And I know off-chain computing has been around for some time, and it's very important for scalability. But I know our framework is very useful for AI. Can we maybe go down the rabbit hole and explore this in depth? How is ROFL a game changer for decentralized AI?
Sure. So I think one thing that Oasis believes is that verifiability will be important, especially as decisions taken by these AI agents start to affect a lot of value. So maybe currently this is not the case, but as we see a proliferation of AI technology everywhere.
Okay, we lost your name. Give us 1 second.
Ooh, okay.
We work in a tech
back?
company. Yes, we work in a tech company. Things like this happen.
Am I back?
Yes, you're back, Ernie. I can hear you perfectly.
Cool. No worries. Right. So that's why it's important that we can actually verify that these interactions are real with the designated AI agents and so on. And in essence, this is what ROFL enables. So it enables that any off-chain computation can be easily verifiable on-chain or to other off-chain agents. What does that mean? So that means that you can have arbitrary programs that you can verify remotely that they are behaving correctly. So basically that they are executing the exact machine code that you've decided that they need to run. And this machine code, of course, can include things like AI models or logic to evaluate AI models. So once you have verifiability, you can this makes it possible to lock private information and only release it to authorized AI agent instances. So this can ensure multiple things. One important thing is that AI agents can have private state. Like without that, everything is public. So all the thoughts or memories, so to say, that you put in would be public. And the other thing is that users and also other agents, if we imagine that in the future there will be probably most interactions will be between AI agents. So we will just specify high-level goals, and the AI agents will interact between each other to achieve the desired outcomes. And obviously, each of those agents will have their own private state, and maybe they will not want to disclose everything to each other, and so on. And this cannot be realized without mutual verifiability, remote verifiability, so that you can actually establish identities of these agents and they can authenticate to each other. Because currently all of your interactions with the agents, like imagine various personal assistants, it's viewable by whoever is hosting those agents. And of course, as usage of these AI features grows and more interactions depend on the AI agents, this becomes more and more problematic. So what ROFL does, it basically abstracts things like remote attestation, light client verification, freshness assurance, rough trusted time, provisioning of these applications, and then also authentication to on-chain apps or other off-chain agents. So basically all of these under the hood things that are required for secure verification of off-chain computation are handled by ROFL. Which obviously makes it very easy to use, and as you don't need to worry about how all of this verification and security assurance happens in the background. But of course, all of these components are very important to be implemented correctly, otherwise the whole thing breaks down and there's no security. So fortunately, we have some experience with building these things called trusted execution environments. And this is just an extension of that, bringing all of the security know-how together with this. And obviously, we want to make it as simple as possible to integrate, both on the on-chain part and then also on the application, off-chain application part. So we want to make sure that, because otherwise things are not actually used. So imagine in your smart contracts, you can basically call a single precompile to verify that the originating transaction was actually signed by a specific valid ROFL app instance. And then ROFL apps can be deployed by anyone given enough stake. So there's some stake requirements and then can be governed by either single entities, DAOs, or arbitrary governance structures. And yeah, this makes it really simple to use in the contracts, and then also simple to write off-chain applications. We'll be rolling out an SDK and a simple tutorial that shows how to actually use it and build cool stuff with it. Also, the ROFL apps themselves inherit this cool thing, and this is that they can support any TE technology that is supported by our Oasis SDK. While currently this is just Intel SGX, we will follow up shortly with TDX support, which makes it possible to have more complex workloads and then also other TE implementations. And the nice thing here is that the core framework will stay the same, so it will be basically seamless for anyone to adopt these additional technologies depending on the use cases, without thinking of, oh, what is all of this that needs to happen to implement authentication and remote attestation correctly, and so on. And then, of course, this together with I think there's also a thing that I've mentioned in the past, and this is GPU attestation. So the more recent GPUs from NVIDIA have support for these. So basically, they have encrypted memory, and they can attest to the CPU to basically you can verify that they are actually running the correct code. And together with ROFL and TDX, well, you can basically evaluate complex AI models inside ROFL apps. And so their outputs can be leveraged by users or other agents, either off-chain or on-chain, as I mentioned. So they can be more trusted than if you don't have verifiability. And as I mentioned, as the value that is governed by this AI agent grows, it will be very important that things are verifiable, because otherwise an adversary can basically compromise such an AI agent either by injecting their own like a completely different model, or faking the outputs, or like using different data as inputs, and so on. And then this can result in wrong decisions and loss of value, which is obviously not something that we want. And also the same mechanisms also allow for things like tracking provenance of data used in AI models, and then also like things like compensating data providers. So all of these use cases are actually made easier by using very through these and ROFL. So hopefully, I don't want to go too much into technical details here, but obviously if people have questions, we can always answer in depth, and we'll also be rolling out the SDK and the tutorial very soon, so people can actually try out all of these things themselves. Yeah.
I'm very happy to hear that, because people have already been asking about an SDK and, of course, documentation for ROFL. So
part of that is on me.
I can imagine how busy you are, Irene, and everyone else in the engineering team. But yeah, I think this is a very elegant and useful solution, because there's a lot of negative thought regarding AI and blockchain. Like a lot of people don't see the use for blockchain when it comes to artificial intelligence and large models. But this is perfect. Like do everything on chain, and only the verification on chain. So off chain and on chain. Sorry. But yeah, as we mentioned, the ROFL is not useful just for AI. Could we maybe explore more use cases? Because as I said, I'm sure a lot of projects are not even aware of what can be done with this.
Sure. So yeah, basically ROFL in its essence is a generic thing, right? It's not just limited to AI. But basically, any kind of computation can be proven on-chain through the use of remote attestation and all of the other security technologies, and that is transparently handled by ROFL. So developers don't need to concern themselves with these details, but just focus on the application logic. So basically, there's a lot of things. For example, you can have various policy decisions that can be computed on-chain and be based on state like payments, NFT ownership, or other forms of access control. And then ROFL can be used to enforce these policies for any off-chain applications. So for example, you can have more secure oracles, like oracles that can interact with the external world in arbitrary ways. So for example, the most trivial example is just, like fetching external information and making it available, of course, in a verifiable manner to on-chain smart contracts, to like things like price feeds, but also any knowledge of external events. Even this can be also combined with AI, so that maybe like a certain AI model is post-processing the raw data and doing some aggregation, and then only posting the final decision or result on chain. So you can have smarter oracles and more secure oracles, because you can ensure with ROFL that each of the node operators is actually running the exact correct code. and even they cannot influence what the result is. So that's one thing. Then, of course, in a similar manner, also things like more secure bridges, where bridges are basically a way to pass messages between different chains or different implementations. They can be made more secure and faster through ROFL, because you can have higher assurances that, well, the node operators cannot actually interfere with the process. Well, they can deny service, but they cannot actually tamper with the values. And the problem with some of the bridges, right, is that the implementations are like the light client verification is sometimes not possible, or is requires a lot of resources, or is just too complicated to maintain to be able to like put it on chain in a smart contract. So you want to keep some parts off chain, and then in this way with ROFL you can actually have some components that are off chain but are still verified on chain through remote attestation. Obviously, you wouldn't want to rely just on a single node, but have a committee of nodes and so on. But this is what ROFL enables without needing to think about how to securely verify all the things. Then also like things like MPC schemes. MPC as in multi-party computation, so schemes where multiple parties are holding, for example, key shares, and then they need to work together to compute a result. Well, this can be made defense like more secure by just leveraging ROFL apps, where you have each party running as a ROFL app instance, executing inside the TE and doing the MPC computation there, and then still aggregating the results. So you have the best of both worlds. Then anything, for example, that requires private computations, for example, on graphs. You can imagine having like a social graph or a financial transaction graph or something that needs to be analyzed, but maybe you don't want to reveal all of the nodes and edges because that is private and valuable information. Like who are your friends, or who you are lending your money to, or what are certain contractual relationships between the parties, but you do want to do some analysis, and this is possible through ROFL apps. You can basically disclose parts of the graph, do the processing inside of ROFL apps privately without even the node operator knowing what the graph is, and then just posting the aggregate result somewhere else or on chain. And then, of course, well, there you can also have something like a marketplace for verifiable off-chain computation that is under the hood, backed by ROFL. So basically, you can imagine buying, compute, but verifiable compute where you can run arbitrary code. And then you just buy it on chain, you prove that you've paid, and then, well, just execute the computation through ROFL apps. And the ROFL part makes it possible to verify that the node operator is actually running the exact code that you've said that it needs to run, and they cannot actually interfere with that. So that's also a very powerful tool. And yeah, this also enables all kinds of defense in depth through zero knowledge proofs, where maybe you have some private state, but you want defense in depth. So you will compute your proof inside the TE and only post the proof externally. So that even if, for example, there's some catastrophic failure, you would still have the ZK proof. So you can layer these defenses on top of each other. Depends, again, how much performance you're willing to pay and so on. But the nice thing is that you have all the freedom in choosing what you will do, because with ROFL, anything is possible.
So could this be used for a marketplace for AI models as well?
Yes, of course.
I mean, it could, right? Yeah.
Like it could be combined, right? So you have like a marketplace for verifiable off-chain computation, but like the models need to run somewhere. So you can have basically you want to run a specific model, then you automatically in the background, you buy compute, you run the model there, and you're using ROFL to verify that the model is actually running. And then you're just, submitting queries to it, making sure that it's actually the model that you've paid for is running. And at the same time, you can also make sure, right, that the maybe whoever contributed the data, right, to train the model wants to be compensated. Like this is a problem even with current foundational models where there are people complaining that their copyrights have been violated by being incorporated in these models and being reproduced in a way that they did not allow. But in this case, this can be tracked, right? This is like provenance can be tracked, and these authors could be compensated for contributing the data, so they wouldn't be complaining.
I actually wanted to ask this, and I wanted to mention this: people getting compensated. Cool. Yeah, there's basically unlimited use cases. we need to break down this into Twitter threads, into complex Twitter threads for each application. Okay, so one other thing that I found fascinating was the introduction of threshold secret sharing, CHURP, where key manager nodes basically hold only shares of a master secret, and this means a bad actor would need to compromise multiple nodes at the same time. Could you tell us more about this?
Good. Yeah, you're getting good at this. Maybe next time you don't need me to explain how CHURP works. Yeah, that's exactly right. So I think this is one of the initiatives that we have where we basically want to, over time, increase the resilience of our network. And this applies to all the parts in our technology stack. So the introduction of CHURP is specifically targets improving assurances around key management. So basically, what is CHURP? As you said, Minya, so CHURP is an MPC protocol, so multi-party computation, where basically stakeholders, this would be, for example, nodes or node operators, need to cooperate in order to derive secrets or perform other cryptographic actions like maybe signing messages. And each node here only holds a single key shares. So basically the root keys are never stored in memory on any node. So they're not stored even in encrypted memory on any node. And through the MPC protocol, only derived secrets can be reconstructed by the client after obtaining the threshold of key shares, so enough key shares from different nodes. Why is this cool? Well, because as you also mentioned, compromising the TE on a key manager node does not reveal secrets, as each node only holds a single share. And knowing a single share gives you nothing unless you compromise a threshold of nodes holding shares. So combining basically MPC with TEs is strictly additive for security, right? So basically even the node operators, if they want to collude, they still need to break the TE, because, well, they cannot access the key shares. So it's defense in depth. Right, so this is definitely an improvement for our key management system. And this also unlocks another feature. So until now, it made no sense to add multiple different TE hardware implementations. Why? Well, because if each of those can get the whole secret, you just need to compromise one of them. So you will just go after the weakest one. Well, and you obviously don't want that, right? Because that reduces security. But with CHURP, basically adding multiple TE hardware implementations becomes additive to security. So then an attacker needs to compromise multiple TE implementations at the same time, so in the same time window, in order to be able to extract secrets. So not just compromising different TE implementations, but also different nodes, so node operators, right? So different entities, which is assumed to be hard in a sufficiently decentralized system. So yeah, that's why also we're looking into adding support for new the implementations beyond FGX. Now after CHURP.
So the attacker would also need to know which exact node to compromise, right? Or it doesn't matter.
Sure. Yes, it would need to be like the nodes that are in the active CHURP committee.
Okay, yeah. And this would
and obviously
have to
CHURP
be
is
done.
doing also resharing of the key shares, so that the shares are not the same all the time, to basically defend against adaptive adversaries, because the assumption is that an adversary can slowly corrupt nodes, and then so
this is basically uncrackable.
Well, nothing is uncrackable, so we shouldn't say
nothing
that.
Is uncrackable,
but yeah, we can make it sufficiently hard for this to be unfeasible.
Nice. Fascinating. I don't think I've missed anything. I think we went through all the most important upgrades. Is there anything I've missed? I don't think so. Yeah,
I think we've covered the main things.
Yeah, we've covered the main features.
If anyone has like more in-depth questions about any of this, feel free to ask them.
Of course, you can find us on Discord. Most of our engineers are on Discord, so any questions you have for us, just join our server. We're there to help you out. I think we have no live questions from our audience. As usual, we're way too technical. But no, this is actually very useful because we can transform all the content into nice blog pieces, Twitter threads, so it's easier to understand. So basically, we can start to wrap up the event. But my last question would be related to the future of the network. What would be the next steps following this upgrade, and what can we expect to see in the future in terms of improvements to the network and of course security?
Right. Of course, I guess there's some immediate steps, and as you said, like people are anticipating finally the release of the ROFL beta SDK with documentation and tutorials for early developers to play with, and this is something that is in the immediate future, that we are hard at work at shipping. So that is the immediate next thing. Then after that, also things that I mentioned, so support for Intel TDX in ROFL applications, and support for things like GPU attestation with NVIDIA GPUs, where we actually have internal experiments that are running some of the recent Llama models inside these GPU-Ts and performing the attestation parts. So we can finally then connect the whole thing and have true native AI agents inside ROFL applications. Then there's also the thing about ephemeral runtimes that I mentioned in one of the past town halls, where there's again some optimization work to be done and so on to support all of that. But obviously, as I mentioned, for gaming and anything that has ephemeral sessions, that will be quite useful, and also can be combined with ROFL and off-chain parts as well. So that's slightly more longer term. So immediate ROFL, ship ROFL. That's
ship ROFL. Ephemeral runtimes
are
also
talking about, like, the core platform. Obviously, like other parts also have a bunch of things on their plates around improving experience for users and developers in Sapphire and so on.
Yeah, I know Tadej has a lot on his plate as well. Basically, all the departments are working hard to improve everything. So,
and also all of our partners in the ecosystem, again, a big shout out. Yeah.
Yeah. Of course, we need to mention everyone. Well, I think we can wrap this up. Thank you for joining us, Jernay. I know you're very busy, so thank you for taking the time for
thank
this.
you for having me. I'm glad to answer questions at any point.
No, but I just love doing this, and we started last year, like this sort of events and being transparent with the community, and I think this is very useful for everyone. Well, we try to do this as often as possible. Our bandwidth is limited, so but yeah, thank you everyone for joining. I hope you had a lovely time. I hope you found this interesting. As I said, like we'll try to create content based off of this. So check out our socials. Keep an eye out on our Twitter, our blog. Our marketing and content teams are pushing content all the time. Again, thank you for joining us here, Nay. Have a lovely day, everyone.
Yeah, thanks everyone. Thanks, Mina, for having me.
Bye.